Here's another example, actually one we've saw before. It was a first example of a linear transformation from R2 to R3. Back in the notes, we gave it by take an input vector in R2, xy, and get the output x plus y, 2x, and negative y as the three components of R3. So let's find the rank, the nullity, and the null space and the range of this. Notice that those are four different things. Rank and nullity are numbers. Null space and range are going to be actual vector spaces given as spans. But first we'll find the matrix representative of T. That's what we need anyways. And we'll do that with the standard bases. That would be just 1, 0, and 0, 1 for R2. So plugging those into T, we get the outputs 1 plus 0 is 1, 2 times 1 is 2, and negative 0 is 0. And then for 0, 1, we get 0 plus 1. We get 2 times 0 is 0, and negative 2. So that's our, we just write them as column vectors with respect to the standard basis again. That's our 3 by 2 matrix. M is equal to 3 rows, N is equal to 2. And that's what we'd expect because it goes from R2 to R3. So notice this is just the matrix of coefficients of a system of equations, x plus y, 2x, and negative y equals, and we don't have a constant in there yet. So it's like the matrix of coefficients of a system where we haven't put in 0, 0, 0, but that's basically what we're going to do next. So a linear transformation just gives all the outputs of a system of linear functions. Like if you set them equal to something, then we'll be looking at a specific picture. But a linear transformation is basically just leaving that open-ended and letting you plug in inputs. So we want to figure out which of those solve, or which of those give you an output of 0. So we'll solve the augmented matrix equation with zeros and get the row reduced echelon form of that. That's pretty fast. First thing I did was let's see, what did we do? I guess we just took row 2 and subtracted 2 of row 1 to get a 0 underneath there and a negative 2. And then notice that I have the, well, divide that by 1, and I do have the same second 2 rows. So once I divide it by 1, I need to get rid of the third row. So I add 2 of that to the third row and get zeros there. Could have done that first and just subtracted row 2 from row 3 to get zeros, and then divided row 2 by negative 2 to get a 1. Either way. And we also get a 0 above that by subtracting row 2 from row 1. So we see row reduced echelon form has both columns with a pivot, and it has a row of extra row of zeros. But there's no contradiction there since it's equal to 0. And so since there's both columns have a pivot, then there's only one solution to AX equal to 0, and that is the solution that X is equal to 0 and Y is equal to 0. So I write that as the null space of T is equal to the 0 vector, just one solution, which is 0, 0. Then I went back and wrote that the rank of T was 2, since there's 2 pivots, and that happens to equal N, which was smaller than M, which was 3. The nullity of T was equal to 0, since the null space is equal to 0, there's no linearly independent vectors in there. And the range of T, I go and take, for each of those pivots, I take the original column of A, 1, 2, 0, and 1, 0, negative 2, and write the span of that. We also know that the range of T does not equal R3 because the rank is 2, which is smaller than 3. And so we know that this is not onto. It's definitely got the rows are linearly dependent because of that row of all zeros, or the rows of the matrix A, the row of just 2 zeros, makes it linearly independent, even though the columns are linearly independent, or makes the rows linearly dependent, even though the columns are linearly independent. Two more definitions here, and then we'll do more examples. So here's a definition. Two square matrices, so both n by n, are called similar when there exists a third matrix P, which is also square, and it's invertible, and A and B are similar if B is equal to P inverse A times P. So that works both ways. We would also say that A is similar to B in that case. So this is basically a way of describing something we've already seen, where you could have a change of basis matrix. And for a linear transformation that goes from V to V, so a transformation from a vector space to itself, and two bases of that vector space, you could write that linear transformation using the basis B for input and output, or the basis C for input and output. And if you do it with B, it equals doing it with C, but sandwiching it with change of basis matrices. So the matrix representation using basis B for input and output equals, first do a change of basis matrix, or transition, as the book calls it, from input in B and switch it to C. Then do the matrix representation using C, multiply by, and then multiply by the change of basis that switches, takes the answer in C and switches it back to B. And that's P is the change of basis matrix, B is C, and P inverse is the other one that goes C to B. And similarity means really the same linear transformation, just with respect to different bases. So it turns out that similar matrices, any kind that we look at, will all have the same features, the same rank, the same nullity. They'll both be one-to-one or not. They'll both be onto or not. And they'll have the same eigenvalues. Asterisk, we'll be talking about those next. They'll also have the same determinants. The determinant of P inverse AP is going to be equal to the determinant of A. So this is the one we call B if they're similar. And next we'll see examples.